Okay, starting from today, we're going to get into geospatial. So the last couple of weeks, we have covered the basics about Python, and then the last lecture we still talk about NumPy and Pandas. So those are basically the building blocks for Python programming. But although we have covered some of the coordinates stuff, those are not really geospatial yet. It's just text information. But starting from next lecture, we're going to talk about really handle geospatial data. And so this is going to be very helpful if you have been dealing with all kinds of geospatial data manually or using desktop GIS. Now you're really going to learn how to deal with this programmatically, how to do things automatically and in a much more efficient way. And so I want to cover a lot of packages. Some of those are very popular in the geospatial community. So if you, in the future, if you need to work as a GIS analyst or you want to do your PhD or master, and if you know, say, I know Python, then you need to know some of those geospatial packages. So basically, they're very popular use, and some of those are relatively new. Some of those might already have a long history. But I want to cover from the basic one, the most popular one, and then slowly getting into some newer version, newer one, packages that are also very popular and very powerful. So for today, I want to talk about GeoPandas. Okay, and if you go to the website, number 9 here, get started. So here, this is some basic information. And so I'm going to cover some of these. We might cover more. Right now, this is what my initial plan to cover. But if we have more time later, we will cover more packages later on. And GeoPandas is for dealing with vector data. So basically, think about GeoJSON, swap files, some of the things that you have been dealing with in desktop GIS. And there's another one called raster.io. That one is for dealing with raster data set, SETA imagery, aerial imagery, basically raster data. X-array can also handle raster data, but it's more like multi-dimensional. That one is also very popular for doing weather and dealing with weather and climate data. And DeepMap is for doing visualization, interactive mapping. So this is the one that I created. But it also supports the Map Libre. So Map Libre is for doing 3D mapping. Okay, and white box tools is for doing geo data processing. So this one is similar to, for example, QGIS processing tools or ArcGIS toolbox. It has a lot of tools that allows you to run things automatically. Gmap is for doing Google Engine cloud computing. So it's also very powerful. I also created this one, and also Segment Geospatial. It's for doing automatic segmentation using satellite data or aerial imagery, and a couple more later. If these are all new to you, that's fine. Don't worry too much. We want to learn all of this, and hopefully after a couple of weeks, you have a good understanding of the Python ecosystem for doing geospatial applications. From there, you can explore. So once you have the foundation, once you have the basics, then you can start going online source and find out the source code, find out examples, and then you can copy paste to your local environment or to the cloud and start making changes, and then you can deal with things. So you don't have to build everything from scratch up once you understand the basics. And so for this, all these packages, you can install using Mamba. So again, we have covered that in the first, I think the second lecture about installing the packages. So you can create a new contact environment, but I assume that you already created. And so what I recommend is to install this one. Mamba install contact for geospatial. I think previously we might have installed LeafMap or Gmap in our first lecture. But in order to use all the packages, I recommend using this one called Geospatial. So it's very easy to remember. And this is the package that I created last year. It allows you to install all the popular geospatial packages. And you can follow the video here if you want to install it, but it's basically just one command line. And here shows you the entire list of packages available. So most of the geospatial packages that are commonly used, you will be able to install just using one command line here. And you can also install individually. I will show you how to do that later. But again, just open in a contact prompt and then just activate your contact environment. If you have Mamba installed, then you should be able to just Mamba install contact first and then the geospatial one command line. Again, there's a video there if you're having difficulties, or if you run into any issues, You're always welcome to ask questions on the GitHub repository. Again, and here under the discussion. So if you have questions, you can ask in here. You get response pretty quickly. There are a lot of people asking questions. So make sure that you utilize the discussion board to ask questions. And after that, you can try it out. For example, leaf map. We will not cover this one today, but so just so you know, right? So this is the website you can see here. It's actually interactive, so you can create the maps easily using leaf map. That one we cover in the next couple of weeks. For today, we're just going to cover GeoPandas. So you'll be number 10 here if you click GeoPandas. So we're going to go through this one today, and the website has been built so you can actually see all the outputs from the website, just like what I showed you last time using the pandas. So you can actually see all the outputs, and if you scroll down, you should be able to see some maps. For example, create some of these maps using GeoPandas. Static map, a static map. You can also create interactive map. So if you zoom in and zoom out here, this one is rendered on the website. Everything is created automatically. I didn't have to create a website. I actually just push a notebook on GitHub. We run the notebook and then install everything, and then you will render the notebook as HTML. And yeah, really nice. Not the focus of this class, but just let you know, website is all the source code. Again, welcome to go to GitHub. Everything is stored here. All the source code, all the notebooks, and the website is being created automatically using GitHub. So this is what we're going to cover today. Really get into vector data processing and visualization using GeoPandas. So what you need to do is to, again, clone the repository. One thing I would like to point out here, there are a couple questions regarding how do I get the updated repository from GitHub. And so after you have cloned the repository, if you have tried things out on your computer and you have messed things around, eventually you're going to, on the left side here, if you see like if you clone from my repository, you can get the updated, but you cannot push back to my GitHub repository because you don't have the permission. But if you want to get an updated one from my GitHub, because I update it every day, so that you don't have to clone every time, then what you need to do is to, again, you come to here, you want to see the changes. So if you accidentally have clicked this one, stays all changes, you're going to have some, maybe let me remove this one. So on your VS Code on the left side here, if you have something stays changes, that means these are changes already you're trying to commit to GitHub. We haven't covered really how to use Git yet, so you're not supposed to do this. So all you need to do is just click this minus sign to move that from the staging area. Staging area means it's kind of ready. You want to push to the repo, but you don't have the permission, so don't do it. And from here, you're going to see this is the files that you have make changes. And if you want to get the updated one, for example, on the lower left corner here, if you see like make, and you say doesn't allow you, or you can go to upper right corner here, and then just say pull. It might allow you, or it may not, because if you have something like in the stage changes, it might not allow you. So what you need to do is basically just click this undo button. Basically discard all the changes. Then now your repo is clean. If it's clean, then you can synchronize with my repository. Otherwise, you're going to show errors. So right now, everything is clean, so I can just say pull. Then you pull the latest changes so that you don't have any error messages. So after that, then you can go to, for example, this folder here, and I can click GeoPandas, right? So this is the notebook that I updated it. And after that, you should be able to see the new content. So you don't have to go to GitHub to download every time. You don't have to clone every time. You can make changes if whatever you like, but when you're ready to get my updated notebooks, just discard all the changes on a local computer. If you really want to keep your stuff, you copy the file to somewhere else. But this repo should be clean. Don't mess around, otherwise you need to delete the repo and then clone again. Questions? Okay, so now let's get into GeoPandas. So again, you can run this one and on Google Colab. And here's some of the concepts. We are going to actually just go directly into the examples. So GeoPandas, as you can see here, it basically is just a table, tabular data with geometry. So all you need basically extend the pandas data type. For data frame, this one is called geo data frame, and it's going to have a geometry column. You can have multiple geometry columns in the data if you want to, but usually you can only have one active geometry. So this is where it indicates this file is a geospatial data. So for example, if you open a shapefile in QGIS or ArcGIS, right? By default, it's not going to show you the geometry column. That one is hidden, but it's there. That's why it's called geospatial data, because without the geometry column, it's not geospatial. It's just Excel or CSV. It's just some tabular information. It's not. You cannot put it on the map unless it's some geometry, geospatial data. Again, we need the GeoPandas. If you have installed using the geospatial package, you can do that. Otherwise, you can just control slash. Then make sure you select the kernel, whatever kernel you use. I think I already installed, so I don't need to install this one again. And I can comment it out. So after that, let's just import the libraries in here. Hopefully it works. If it doesn't, that means I don't have that installed. Then I have to install that. And GeoPandas sometimes can be tricky. It sometimes like installation might not work on certain computers. Then okay, it works on my computer, so that's a good thing. And so we import this one, GeoPandas SPD. This is what we learned from the last lecture. The second one is the convention is this: import GeoPandas as GPT. This is usually what people use just as shortcut. Also wanted to use a matplotlib. Okay, so this is a library used for doing visualization of data. It's also a very popular one. We don't have time to spend a whole lecture covering this one, but we're going to use it from time to time when we're using some other geospatial packages. So just pay attention. This is also a convention. You're going to see this one a lot online. If you go to source some Python code, it's going to show you, it's going to create maps, create graph, and all kind of things. So matplotlib .py as PLT. And this is PLT is going to create a map with a canvas, and then can do all kind of things on that. So once you import the libraries, then we can start creating some data. Were you able to import this one? Okay, that's good. So next, let's create some geospatial data here. And now you should be familiar with this one, right? A dictionary, and then with keys. So basically the key basically is the column name, right? The city with 4 rows, right? 4 records, and with a latitude column and a longitude column. And last week we talked about this one, right? The data frame. So you can convert a dictionary to a data frame, but it's not geospatial yet. Let me separate this one into 2 so that you can see the differences. So I'm gonna cut this one and do it in here, run it, and then just type df. So look at this. So right now, this is just basically just like a CSV, an Excel spreadsheet. It's not geospatial. You can see the 2 columns, latitude and longitude, but there's no geometry column yet. And so we're going to use the gpt.geo data frame. So you're going to see this one, and the input can be a data frame. So basically, we're taking this data frame, and we're going to assign a geometry. So the geometry in the geo data frame, there's a function called gpt.point from xy. So this one is similar to, if you ever use ArcGIS, like xy data, xy. So if you click, and then it's going to ask you to select a file, and then from there, it's going to ask you to select the column. And so from xy, you can pass in basically 2 lists: df.longitude and df.latitude, right? So basically, take this entire column, the latitude column, longitude column, and also latitude column. So if you really want to see it, for example, I can df dot longitude. Oops. So there are different ways you can do that. You can just use the dot notation, or you can use square brackets. So either of this one is fine. So df, for example, here, latitude, they are the same. Okay, so you can use either way. Df dot. So basically, it's an attribute of the data frame. And so this is the way how you access the column data, right? So it's a spread, just like you open a CSV, you select that column. And so what we're doing here is use this geometry property. So you can take a plain CSV data, and then say, okay, I want to also create a geometry column, and that geometry column is going to be created based on the points of log 2 column, based on the latitude and longitude, right? So if you have a point here, latitude, longitude, it's going to create a point. So we're going to end up with 4 points. And this is how it's being created, like this. So right now, if you run this one, you should be able to see, right? So now we have a geometry column, and this one doesn't. And this geometry column is where it indicated right now this is geometry. So if you want to see the data type, I can create a new row, GTF.columns, for example. You see we have 4 columns, and you can also GTF.d types. You can see the data types. So the cities is an object, basically it's a string. Latitude is floating point, is number, and then floating number. Last one here, you will see this one is called geometry type. So it's the one unique to GeoPandas. Pandas doesn't have this data type, doesn't have the geometry. So only geospatial data, GeoPandas, is this one. So right now, this one becomes a so-called geodata frame. So it's a data frame with geospatial data called geodata frame. And you can treat this one as a shape file. It's a GeoJSON that you open in GIS. And so later we want to see how to access this one. Most of the time, we don't need to really to create this one by ourselves to create points. You can just read from existing file. So you don't have to create data from scratch. But you certainly can if you want to. Just like if you go to ArcGIS, QGIS, you can create a new shape file. You can start just doing digitizing. This one you can do the same thing. But most of the time, you're just going to download some data. You want to open the data in GIS. So we can do the same thing later. I will show you some example. But for now, let's assume that, okay, this is the data. So if you really want, I think from here, you can actually, maybe I'll show you later. For now, just look at, this is geodata frame. This is geospatial data now. So we create the data. The next example, we're going to read some real data. So you can read the data from the internet, or you can read the data from your local computer. So for this example, I just provide the HTTP URL. So this is from my GitHub repository. It's the New York City, for example, boroughs, basically the boundary of the boroughs. And you can just use gpt.read file. So this is one function, read file. And then just provide the URL or provide the file path. And then you can just display it. So without the head function. So we talk about the head function in the Pandas lecture. Basically allows you to show the first 5 rows, for example. And so this file is maybe a couple megabytes. And now take a look. So it's just, oh, it's just only 1, 2, 3, 4, 5. Yeah, only 5 records. So look at the one on the right here. This one is called multi-polygon. Okay. So the data type, the geometry type, we're going to have point, line string, polygon, multi-polygon, or line string, multi-line string. Those are the common called the shapely all the feature collection geometry type. We use more examples later, but for now, just let you know this is basically just polygon. But sometimes a polygon can be multi-polygon, can combine as a single polygon, basically composite polygons, and just show it as one record. Kind of like, for example, Hawaii, right? How many islands? How many islands in Hawaii? Right? At least 3 or 4, right? 4. But it is just one state, right? In the US. You don't have 4 rows when you open a state boundary. It's just Hawaii, and then you have 4 polygons. Those polygons are separated, and it's like multi-polygon because you can have one row of record contains multiple separated polygons. Kind of like, for example, continental US, right? You can have Alaska and also the contiguous US, but you can combine them as a single one. So if you're looking at a country, for example, global countries of all the countries together, US is just one line, then you also called multi-polygon. We encounter this more later, but look at this, how easy it is. So this is kind of like you drag a file into QGIS or ArcGIS, and then you open the attribute table. Right now, we are just use GPD to read the file, and then just pointing to this one. If you have a file path on a local computer, you can also have the file path. For example, you can do it like this if it exists. Or you can have, if on Windows computer, you can have R, and then to your C drive, D drive, whatever, where the file path. So it's up to you to provide the file path. It can read from the internet, so it's very convenient. And after that, it's going to return GDF, so geo data frame, so just basically a variable name. It can be anything else. It doesn't have to be GDF. And so once you have this file, you can do all kind of manipulation. You can select certain files, and then after that, you can write the file back to a computer. So if you want to write a file to your computer, you can do it like this way. So you can specify the output file name, and then just use this function called, because this is a geodata frame that we get from the above, right? Although we haven't done any changes yet, we're just reading the file from the internet, and we haven't saved this file to a local computer. So if you want to, then you call this function called to file, and then just provide the output file name you want to use. There's also a driver in here. Driver basically means to tell explicitly what kind of file format you want to use, but you don't have to provide. You can ignore it. GeoPandas is pretty intelligent. It's going to infer the file format based on the file extension. Because above here we use .geojson, so GeoPandas knows it's a GeoJSON function. So you're going to use the proper driver for that, and then that's it. So basically, it's basically just one line of code. You can directly put the file name in here if needed, and just run it. On the left side here, you should see this one showing up on your VS Code, right? And double click it to open in VS Code, and look at this. Wow, it's pretty complicated. There are all kind of coordinates. So basically, it's just each polygon. It's very detailed. There are a lot of polygons. But this is so-called a GeoJSON. So you can open a GeoJSON in QGIS. I'm not sure if you can open directly using ArcGIS. But this is a very common geospatial data format. GeoJSON is plain text TXT, and it's very easy to be to use in all kind of desktop GIS or programming languages, because it's just you can even open this one using just the Python open, and open the file just like you're opening a TXT, right? So previously we covered how to open TXT. This one is basically just a TXT. It's just a plain text. You just need an editor. You don't really need any specialized software to open. But for shape file, you cannot. You need desktop GIS to open because it's a binary format. You cannot just use VS Code to open a shape file or geo package, because it doesn't work that way. It's specialized format. So for example, here I can open this one, and then let me add a base map in here. And so I can drag this file that we just downloaded. Not downloaded, we read it as a GeoPandas frame, and then we save that to a GeoPandas, and then the file is on the computer. So then now I can open it. So for example, I can go to the book, and then Geospatial. So this is the one that we just saved locally, and drag it directly to the map. And so I'm going to show you blah blah coordinates. Just click OK, and that's it. So I'm going to zoom to this, so it should align directly on the map. So GeoJSON inside there, because it's geospatial data, and QGIS can open it. I forgot if ArcGIS can do that or not, but you can do that later using other data formats. All right, pretty good. So you can see here, this is a very detailed file, and there's a lot of points in there. So that's why you're going to see GeoJSON is pretty detailed, right? So all the points, these are all composer points. So it's being represented as geospatial data. Inside this is called GeoJSON. Okay, so if you want to save the geodata frame to a GeoJSON, just give a file name .geojson. Then it should save it to a GeoJSON. So similarly, you can save it as a shape file, right? .shp, and it's the same function. Again, you don't need to provide the driver, just run it. So pay attention to the left side here, and you save the file, generate it, right? So right now I have this one here, .shp. So this one, you cannot just click here and then expect VS Code to open it. Cannot, because it's a binary format. And this one does need specialized software to open it. And this is where QGIS or ArcGIS can be helpful, right? So, but it's the same file. Right now, I can just come here, drag this file, and then just open it. So now you have this same thing. It's a file. And you can open the attribute table. So this is essentially what you see on here, right? It's the same thing, except that for the desktop GIS, this column is hidden. This column doesn't show up on the software. But the reason why the software is able to display the geometry, display on the map, is because of this column. Without this column, it's non-geospatial data. There's no geometry. So the software can read the geometry, but it doesn't show you that. So all the geospatial data in here is composed of the attribute table, also the geometry. So there are two components. Attribute table is just a tabular data, non-geospatial, and the shape in here under the hood is all the points. And this is why GIS software can handle that. So as you know, it's the same thing, right? It doesn't show in here. You use ArcGIS, you won't see the geometry column, but it's the geometry column makes it geospatial, makes it spatial. So in GeoPandas, you can see all the stuff. So all the polygon you see here, this very complicated. There are a lot of points inside, making a polygon. And also you can save it as a geo package. Geo package is kind of like a database. And I think ArcGIS also support this one. Certainly QGIS also support this one. So later when we use DiffMap, we can also show you how to use DiffMap to visualize all this kind of data. So again, you don't have to provide the driver. GeoPandas will be able to infer the driver based on the file extension. But if you don't provide the file extension, then GeoPandas won't be able to do that because they don't know what format do you want. Right? So you can use the geo package and run it. So now we have this one. So for last data set, if you're doing geospatial, for last geospatial data set, you should use the geo package. Okay? Don't use shapefile because shapefile is like outdated format and it's not very efficient. And also you see why we have to generate multiple files in order to get a shapefile. So .ssp, .prj, .ssx, and .dbf. So those are all the components of a shapefile. But for geo package, it's just one single file. It includes everything. And it's basically just a database that you can do a lot of things. So this is the one. It's prefer data format for geospatial. Large vector data set. If you need data that can store more than 2 GB, don't use a shapefile, okay? Use geo package. For GeoJSON, it's plain text, but it's not super efficient. And the file is also much larger. So if you pay attention to here, right, the GeoJSON one is over 3,600 KB. The geo package is only 1.2, and the shapefile is also only 1.1. So you see the sizing here. The GeoPandas, the GeoJSON file is not compressed. It's plain text file, so it's pretty big, and it's not very efficient. So basically, it's going to take a lot more space. Nice thing, you can open using any text editor. You don't need specialized software. Also, the limitation for GeoJSON, it doesn't have so-called spatial indexing. Spatial indexing is where when you're trying to do spatial analysis, trying to figure out whether each polygon is intersecting with the other polygon or not, it's going to take a lot of time to figure it out. For GeoPackage and also shapefile, they have the spatial indexing built in, so it's much faster. But also the file size is a little bit smaller. The downside, you will need spatial software or packages to handle that. You cannot just use plain text editor or just use Python built-in functions to process the data. GeoJSON, and you don't need any spatial. So for all this lectures we're going to cover, most likely want to encounter GeoJSON, shapefile, and also GeoPackage. So those are the three common formats. Okay. So always remember, if you have a vector data somewhere, you want to deal with Python, then you use GeoPandas to read file. Okay. Once it becomes a data frame, then you can do data processing in a data frame. We're going to show you examples later. And after you are done with the data processing, then just GDF doc to file, and then just provide the file name to whatever format that you want. Then just save it. That's it. So input, output. Then later we're going to talk about in between what kind of things can you do. Okay, questions? Yes. This one right now is in the memory, so it actually doesn't save the file. So if you want to, for example, if where it's going to save the file is you read the file and then you save it, or you are welcome to click this one. It's going to open this in a browser, and then you can save this one to a computer. For example, I can save it to my book in here, and then, for example, to maybe to my downloads folder, for example. We're going to show you ways how to download them automatically. But now, if you want to save the file, this is how you save it manually. Certainly, if you want to download the file manually, I can also do it this way: import leaf map, and then you can just call the leaf map function download file. You also download the file automatically from somewhere. So I can just leaf map download file, and then just passing the URL, where you want to get. So you can download thousands of files automatically if you want to. And so URL, then the output, right? You can just specify where you want to save the file. For example, I want to save this one to my, let's say the downloads directory. Okay. You need the full directory. So you need to go to your C drive, and then your username, for example, your username here, and then downloads. Okay. So what you need to do is, for example, I want to save this one to my computer. Then I can do in here the output equal to, again, on Windows, you need to use R, otherwise it's not going to work. So, right, the file path, and then backslash. So here I can maybe nyc.geojson, something like this. That's it. So if you run this one, you should be able to download the file, show you the status. So you can download it to anywhere you want to. But GeoPandas, it doesn't give you that flexibility. You need to read the file first, and then you can save it using the to file function. So NYC here. Now if I open my folder, you should see this one on my computer. It's the same thing. So GeoPandas download it to the memory using the read file function. But you can always use to file, save it to somewhere, to whatever data format you want. And we do the conversion. So basically reading the data, and then it's already been converted to a geodata frame. The geodata frame can be saved to any format that you like. Okay, any other questions? So next, let's talk about how we do some simple, basically access the data, right? We have load the data, it's already a geodata frame. And so the first one here, I'm going to show you the differences. So let me show you one more time here, GDF. So this is what we have right now. And the GeoPandas is a function called setIndex. SetIndex is the one that, okay, it's a unique column, has a unique ID, and that ID can be used like as a unique ID. It's kind of like, for example, your net ID, your social security number, those are unique. So you can, if you have that column, you can set that column as an index. So later when we do the mapping, we automatically use that one to do the label. Okay, if you don't set the index, you will just say 0, 1, 2, 3. If you're on the left side here, you see this one actually is the index right now, 0, 1, 2, 3, 4. But if you can change it. So this is why we use this one here. So here, GDF.set indexing. And always remember, everything is just like things in the memory. So if you make some changes, you will need to save it to override the existing variable. Otherwise, it's not changed. Make sense? So you're making some changes. So don't do it like this. If you're doing, oops. If you're just doing like this, you're just doing something without return. So this is going to have no impact. You run it, and you're going to do it like this, right? So right now, this one is the indexing. So basically, it's setting this one because it's unique. Basically, the board name, and that's it. So right now, if I print out again GDF, there's nothing. It's not. It's still the original one. So make sure that if you make some changes, I think there's a function called in place. Otherwise, you need to just say GDF equal to this one. So you're overwriting this file. And if you're showing it again, then you want to have this. This is really what you want. So you're making some changes. You need to save the changes back to your file. And now you see we have this column as the index. So then we can start doing the mapping. Or you can calculate the area. For example, GDF.area. So we're going to create a new column called area. This is GeoJSON. And you can see the coordinates in here. We don't know the georeference yet, the coordinate system yet, but geodata frame has a function called .area. So let me show you. Right, so this is the geodata frame that we already have. You can just call .gdf.area. And see, you see the numbers in here? 1.6 multiplied by 10 to the power of 9. So 10 to the power of 9 is like 1 million square meters. 1.6, basically 1.6 million square meters. And you get the owner number. So this is similar to in use ArcGIS. You can calculate the geometry, you can calculate the area of each polygon. But in GeoPandas, it's just one line, dot area. So now we have this column. But if you want to save this one to the data frame, basically add a new column to the geodata frame, then you can do it this way. Equal to something. So this is similar to what we covered in the previous lecture about pandas, right? So if you can give a new column name. If the column name doesn't exist, we will create a new column. So in that way, you are generating a new column. So if I run this one, oops, borrow name not in column set index. I put it already messed up. So somewhere, so let me read this one. Let me run it one again. Here. Okay, so now I can come to here, set the index, and row name. Oh, I already set it above, so I cannot do it one. You cannot do it multiple times because I already did it, so it's already being removed. We'll run this one more time. Okay, so I'm gonna directly go here. Now it should work. Look at the last column. So now we have the area column, and that area column is the one that calculated directly. If you use desktop GIS, you need to use the tools to calculate the polygon, the area. You can do the same thing for line. So there should be a GF dot length. So for example, you can calculate the length, or you can extract the point if you want to. We show you more examples later. Similarly, you can do the boundary. Yes, the boundary is basically the line, the length of the polygon. You can also calculate the centroid, the XY coordinates of the points, and then we can print it out. So look at this. So now for each polygon, we have the boundary, basically the line, how long it is, and we can also have the centroid, basically the center of the polygon. And then we can start measuring, for example, the distance or whatever, something like that. So let me show you one more time here. So this is the new data frame that we just created, and we have added a couple new columns, right? We have the area, we have the boundary, we also have the centroid. So next, let's talk about how we do the filtering, right? So similar to the pandas, we talked about in the last lecture, you can select a certain row that meets a certain condition. So for example, this one has 1, 2, 3, 4, 5, right? So if in the desktop GIS, we used to be able to just open the attribute table, and then you can just do the selection, right? You can do it like this. So how do we select a column, select a row programmatically using GeoPandas? Let me go back to here, right? So GDF, now you can actually do it like this. I can say GDF dot LOC. So basically the location. Basically, we want to do the selection, and you can select, for example, just the Manhattan. And this is going to give you this row because the location we use this one is the index. So basically what we're doing here, find where the index is equal to Manhattan. So you're going to get this one, and it's going to get the records of all of this. And if you have another one, for example, comma, and then have another column, then it's going to get that specific column. So this one gets the row, and if you add another column, add another things in there, it's going to get the column. So this is why comma and then centroid. T typo here, TR. It's actually just select the point. It doesn't show you because this one is a geometry. This geometry, GeoPandas, when you display, it's going to show you directly something like this. You can change something else. For example, I can change the let's say the Manhattan geometry. Example. So you're selecting the row and then select the column, and let's see what this one looks like. Okay? Pretty nice. So this is exactly the same, just like what we did in desktop.js. You select the row and then it's going to be highlighted. This one basically select that row and that column showing the geometry, right? But the nice thing about this, you can have multiple geometry. So in this geodata frame in here, we have this geometry column. That one is polygon. We also have the boundary column. That one is the line, basically the boundary line. We also have the centroid. That one is the center. So you can also do this boundary. Okay. So kind of like the same thing in desktop.js. Like that, and then you display that, just like. But we're doing things programmatically, and you can change anything. So what you need to remember, g.LOC, so basically the location, basically find out the one is equal to Manhattan, because we have already set the borough name as the index. So that's why it's able to find this one. Otherwise, you won't be able to find the index. So this is how we do the filtering. So we change it to centroid, for example, here. So now we know this is the point. For example, this is the point in Manhattan. So you can think about in the desktop.js, you'll be somewhere here. Open this one and Manhattan, right? So the centroid probably is somewhere around my mouse in here. And once you have the centroid, you can calculate the distance of other polygons to this point. And what we need is just one line of code. So look at this one. So gdf.centroid, that means you're going to get the centroid of all the columns, all the values, this entire one, and then it's going to calculate the distance to this one. Because we have already selected this Manhattan centroid, right? Distance to Manhattan centroid. And then it's going to assign the value to a new column, and then it's going to show you. See how fast it is, right? You don't need to run any two. You just run one line of code, and you can calculate the distance. So right now, because we're using the centroid for Manhattan, so yourself distance is 0, but the centroid for other points to Manhattan specifying here. So this distance function is in GeoPandas. So you can have a column dot distance to a point, and then it's going to calculate the distance. And then once you generate the result, you can save that back to the geodata frame. So it's a very nice one if you need to calculate the distance. So once you have this, again, you can display the whole geodata frame in here, because we have been attaching the result to the entire data frame. So now we have, from the original one, that we only have these 4 columns. But now we have the area, we have the boundary, we have the centroid, we also have the distance. You can keep adding more and more columns to the data if needed. So once you have this, you can easily calculate, for example, the mean distance. So what this one is doing is this geodata frame, I have this column. I want to calculate the mean of this column, right? So all I need to do is just GDF distance to Manhattan mean, and it's going to generate the mean, and it will show you, okay, 44,000. So this is how you do data processing using GeoPandas. So once you are done, then you can save the result back to your computer. So for example, right now this is a data frame. We can do the same thing. So I'm going to add a new cell. Then how do we save the geodata frame to your computer? GDF dot to file, make sense? And then from here, then you can give any file name that you like. So I'm going to maybe say, okay, nyc dist.shp, for example, a shape file, distance. A GeoJSON, you can be GeoPackage, and then just run it. Oops. Multiple geo, we can only select a single geometry column. Oops. So that means you cannot, it doesn't allow you to have multiple geometry columns. Let's try it to GeoJSON. So GeoJSON probably is more flexible. Okay, doesn't allow you. Then we need to select just the column that we want. So in that case, then we need to do it like this. So you need to select the columns first. Let's see GDF square brackets and then square brackets, and then from here you can say inside here we can have the geometry column, and we can also have the distance. What's the name again? Distance to Manhattan. The reason that it doesn't allow it because we have this boundary column. We also have the centroid column. That one doesn't allow you. But the other way, you can actually drop. You can drop the boundary and the centroid column if you no longer need them. For example, I just want this all of the column with the area and also the distance. So maybe let's do it the other way. We can drop some of the columns. So you can do it like this: GTF dot drop. Okay, really interesting. So see this one dropped, and I want the area, so I want to keep this area. Okay, and I want to drop just the boundary and the centroid. So this one here, you can either use the drop and then equal to GTF, or you can use this parameter called in place equal to true. So what this one is doing basically is removing those two columns and then override itself. So right now the new GTF will be just have one geometry column. So take a look, run this one, and then if you execute this again, so right now we only have one geometry column. We have all the previous columns, and we also have two new columns, the area and also the distance. Now you should be able to save this one to a GeoJSON or to a swap file without throwing errors. Take a look. Done. And so if you want, I can open in desktop.js and we can check that. So here, book, Geospatial, and so NYC DST on this one. Okay, now open this one, open the data table. Voila. So we have this new two column that we just created. Right? But we didn't use desktop.js to do that. We used the program to do that. And the nice thing about this, it doesn't matter how many rows, how many columns, you can handle it easily. And you can do a looping, for example, do a loop for tens of hundreds of files. It's going to be automatic. So this is how you can use GeoPandas to manipulate geospatial data. You can do some selection, you can do some calculation, you can create a new column, you can calculate some statistics. All very easy using GeoPandas, just a couple lines of code. Okay, any questions? So now, like, open the file, do something, output the file. So next, we want to talk about how to do plotting, how to actually see that using GeoPandas without having to use desktop.js. And so the first one here, we can actually plot the map. So GDF, so look at this one, GDF plot area. So we're going to plot the data based on the area. We're going to add a legend, and we're going to give a title, and this just run it. See? Pretty nice, a colorful map. And you don't need to use desktop.js to just do all the design. You can customize things precisely to what you want, to your liking, right? So this one, we're adding a color bar automatically, a legend. So if you don't need a legend, for example, this one is based on the area, basically the size of each polygon, area of each polygon. So the yellow color means a larger area, right? The darker color means a smaller area. This is why this one is smaller, right? This is big, and green color in the middle, and also the blue one. So this one basically is just a color place map, showing you the color represents something. And we give a title in here, TLT. So this one is the map plot lib, right? Earlier. So all we need to do is GTF.plot. If you don't provide anything else, you can just like this. It can be as simple as this. So assume that you already read the data into a geodata frame. If you want to see what it looks like and you don't know what to do yet, just plot. By default, it's going to show you some like very basic one like this. It's not super fancy, just like green, dark blue color, yeah, dark blue color with some boundary. But if you need a little bit more customization, so you can give, for example, the plot area, the legend, and then give a size. So the size you can change it. So this is 10 by 6. If you want to be smaller, for example, I can do 5 and 3. So 5 inch and 3 inch is going to be a little bit smaller. So you can see the number here. You can easily customize yourself. And you can give a title. You can change the title. PLT show is just going to show the map. Okay, so this is how we read the file and then plot it. And you can also plot multiple maps, multiple layers together. This one probably doesn't work yet because I delete the centroid. So there's no centroid right now. It's not going to run into errors. So if I want to show you this one, then I need to go back to recreate the centroid so that you can see it. So I'm going to go to, I need to read the file again. If you already deleted it, you can always go back to read the geodata frame again. And then we can read the centroid. Run it one more time here. So I'm going to go to this one and then set the index and also give the area, right? And then I'm going to calculate the boundary and the geometry. Okay. Well, now we have this one, have the centroid in here. We should be able to plot this one. We go back down here and run this one. Now it should work. Okay. So what we're doing here is the gdf.geometry.plot. So basically, we are plotting the polygon first. And after that, you can have the centroid, and then the centroid going to plot on top of the map. And you're going to give a title, blah, blah, something like that. So you can, everything is customizable. For example, the color, you can change the size, you can change anything else. So similar to what we did earlier, I think this one you can just, for example, I can do, what's that, legend equal to true. Let's see if it works. Oh, no. Oh, this one is not the same one as we did before. So the legend doesn't apply in here because we're using just axis, not the original one. Anyway, to keep it simple, right now I just plot this one, just showing you here. We just have a polygon, a point layer overlay on top of the polygon. And if you remember, right now we're all using just one geodata frame. We don't really have anything else. Right? We don't have two data layers. Unlike the desktop GIS, you need to have two data layers and then you drag them together. Right now, we're plotting the same geodata frame, but we're selecting different geometry column, and we can plot this one. You can also plot the line if you want to. And so that's about doing a simple plotting. Okay, so and this one here, if you need to plot multiple data layer, you need to assign this one to an axis, and then so you can think about this is like the base map. And so we can plot the centroids on top of the base map. So this one, you can see this is the foundation, the GeoPandas. So this is based on matplotlib. So we can have a layer, the bottom layer, and then you can overlay things on top of that. Next, let's talk about geometry manipulations. And the simplest one would be, for example, buffer. So look at this one, GDF.buffer, and then 10,000 feet. Because the unit is feet, and that's why you can just do the buffer. So what it does is just like similar to you run the buffer tool in ArcGIS or QGIS. It's going to buffer every row based on the geometry, and then we can plot it on top of the map. So look at this. And the plot function, we also have the alpha here. Alpha means it's the opacity. So that means it's half transparent. So look at this one, right? So earlier we have the polygon, and then we're going to create a buffer around the polygons. After that, we can plot the polygons. GDF, we create the buffer, and then just use the buffer to display that. So again, if you want, you can look at this one. You can display that, right? So it's still the buffer column. If you want to show the entire one, then you just see GDF. See? Right, so basically it's this column. So the buffer column is also a geometry column that we just GDF doc something. So it's going to automatically retrieve the geometry because if the geodata frame, it must have a geometry. Okay, and then you can just doc buffer. You're going to buffer every record in the file. And once you have that, you can do the plotting, right? Just like what we're doing here, simple and easy. GDF buffer doc plot. And then you give your opacity. So this is half transparent, 50%. And the edge color is black. And then give a title, something like that. There's another one here called convex house. So basically, it's the minimum boundary, kind of a minimum a polygon that enclose the geometry. And if you really want to see like what kind of function is available, you can always GDF doc, and after that you can see all the functions available for this one. So we're using only just a couple functions, but there are a lot more things available in here. So there are a lot of things you can apply to a geodata frame. You can save it, you can do manipulation, you can do filtering, you can do selection, you can do all kinds of things. You can save it to the file. So just scroll down here just to, you can also, for example, do overlay analysis or overlay or overlap. Try to figure out, like, use some examples, see what's the differences. You can do the scale, you can do shifting, you can do spatial join, edge join, spatial join. So desktop GIS also has those spatial join functionality. And to something, this is where you can save this one to a file. Even like to HTML, you can save this one to HTML if you want to. So this is convex how. And the last couple example, we're gonna do some like spatial analysis, for example, intersection. So look at this one. We're going to select, for example, GDF dot location and then dot Manhattan geometry. So what we're doing here is we select the Manhattan polygon, and then we can just intersect, figure out which polygon intersect with Manhattan. So on this one, take a look. And all of them, okay, all of them intersect except the Staten Island. So if you go to here, right, so this is Manhattan, right? Everything intersect with this one. There's something like overlay intersecting. It probably is hard to see in here, but this one certainly, this one doesn't. This one. Anyway, so basically it allows you to find out the polygon that in adjacent or intersect with the polygon that you're selecting. So all you need to do is to do this one. So this is equivalent to when you open the attribute table and then select the column, the row equal to Manhattan, and then select the geometry. Once you have the geometry can do a spatial analysis with other stuff. And the intersect function is just to figure out whether they intersect or not. Or you can do containment. So containment means this one is being contained or within. Or is it contain something else, or is it within something else? So for this one, we're trying to figure out, for example, if the center is within the polygon geometry or not. Of course, because we rendered the point within the geometry, so everything is within the polygon. So basically, those 5 points, each point is within a polygon. So the GDF doc centroid and the GDF geometry, GDF centroid is just a point, right? So each point is within a polygon. That's why you get 2 for everything. But it's not always the case. You can have a point layer and then you have a polygon layer. They may not necessarily intersect with each other. Okay. We'll show you more examples in the future, but for now, just to say, you can have some of these spatial analysis functions. Okay. So the last one we're going to talk about is the coordinate system, and this one is super important. So you do really need to know the basics about coordinate reference system, because geospatial data without a coordinate reference system, you cannot put it on the map. You cannot overlay on top of the base map if there's no coordinate system. And so if it is a geodata frame, you can actually track that whether it has a coordinate system or not. So for GDF.CIS, you can check it. So this one here is called Projected Coordinate System, EPSG 2263. So anyone know what is EPSG? No? So EPSG stands for European Petroleum Standard Group, I think. You can just Google it. So basically, it's similar to our projection coordinate system. This is a standard one, and it's a number, so EPSG in here, okay? And you can source any number. So for example, this is, what's the number here? 2263. So EPSG.io, and then from there, you can 2263. Okay, New York, Long Island. So this is a local state plan. So you can see all the information here. So you're going to see the EPSG a lot when you're doing Python geospatial programming, because most of data is going to use some of this so-called coordinate system. It's using the EPSG number. Rather than you have to remember, okay, it's using UTM, North 17N or something like that. It's much easier to just remember this number, EPSG something. So 2263 is the one that's being used in this data set. The other one very common is 4326. 4326. So this is a WGS 84. Basically, latitude and longitude. And this one is not a projected coordinate system. So you need to understand the differences between uh, projection GIS and also the coordinate GIS. Projecting that means it's being projected onto the 2D dimensional space. So it's already being projected. The original latitude and longitude is on a sphere. Excuse me. It's not projected. So it's not a projection, okay? A projection is that you need to unwrap the sphere into put it into the two-dimensional space. So specifically for this one, I am showing here. Oops, sorry. For this one is 2263, and you can convert it to something else. For example, I can convert this one to go to GDF to CIS. That means you can change it to 4326. So the differences between this one, if you open the desktop GIS, it's going to tell you this file doesn't have projection. It's going to project automatically. So look at this one, like EPSG to coordinates. And so right now, if I do it this way, run it. Right now, this one, you see the coordinates. This is the coordinate, latitude and longitude. But if you don't do the projection, you just plot the one directly. One more time, I can do the same thing to the previous one, right? So this one is 2263. So when I do the same thing here, except I don't do the conversion. I just use GDF. And you will notice the differences. So look at this one here, the x-axis, 0.92 to the power of 6. So this one, because it's a state plane, so it's using the feet system. So you see all the numbers are pretty big. Compared to this one, see here, this is latitude and longitude. So sometimes if you need to create a map, if you want to change the coordinate system to this one, you need to do the conversion manually, so that it's going to show up correctly. And if you save this file, for example, like earlier, I show you, we export this one. So for example, if I double click on the file, and if you show the information, maybe show the, yeah, you see, you can actually recognize this one, 2263. So desktop GIS is able to read this coordinate system. But if somehow, if your file doesn't have a coordinate system, for example, this is the one that we have converted to 4326. Now this one is only the WGS 84. It's not a projected coordinate system anymore. If you save the file, if you open in desktop GIS, usually you give you a warning saying that there's no coordinate system. So let's try this one out. For example, I can say GDF and then 4326 to file, okay? And then it's smart. So on this one, oops, geodata contain multiple blah blah doesn't support. Okay, so we need to delete it again. What's in there? I forgot what's the GDF. So one more time here. So we have again we have multiple geometry columns. So I need to drop them. You need to drop the boundary, the centroid, the buffer, and the convex house. So click here so that you can save the file. So GDF equal to GDF dot job. Okay, and oh nice. Boundary. Here another one here. Boundary, convex house. Not these two. So we need to drop 4 columns. Boundary, centroid, buffer, convex, buffer, convex house, and also centroid. Okay. So once you have this, oh no, we are doing that for the, you need to do this for this one, sorry. because it's 4326. Huh? Okay. Hopefully it works now. Okay, now we save the file. So this one, after it changes to WGS84, not projected anymore. So let's open the file, see what happens. This one, right? And let's see if we give any warning. But if you open in ArcGIS, it should give you the warning. But this one doesn't, so you just open it right away. But if you double click properties, see this one, WGS84. So you're gonna see the project GIS and just order just the WGS84. WGS84 means it's not projection, it's just latitude and longitude. But QGIS was able to recognize that. And sometimes if you open data and it doesn't align on the map, that means the projection is wrong. So I can show you an example in here. I can say make it change it to something else. For example, here, just to show you an example, I can GTF this one CIS. So I'm going to show you here CIS is 4326. And sometimes it is not a correct one, you can assign to something else. But you might be making mistakes. So for example, here I can assign a new projection called EPSG 3857. And let's see what happens. So when I open the file, let's see if we can align it on the map or not. So I'm going to open this one. I save this one. And then I'm going to save this file again. Oops. Oh, it's being used. So let me change it to another name. Okay. I'm going to run this one. You're going to save the file. So this time, do you expect it to align on the base map? Let's see. It doesn't come up. What happened? And let me zoom to this layer. Where it is? Oopsie. Nowhere showing on the map. And if you see the coordinates here, pretty big. So where's the global map? It's not there. So the reason for that is because I set it to a wrong GIS. You're not supposed to do that because you cannot just assign it. You need to two projection. If you use the two CIS, then it will work. If you use CIS and you assign one, it's not right because two CIS means you're doing the reprojection. It's just assign a CIS, you call assign a projection. You cannot just assign because the data, although it doesn't have that projection, it's already in a certain value range. It's already a certain format. So you cannot just do it like this way. You're going to having trouble. So this is why it doesn't work in this case. So what you need to do here is actually, rather than assign a CIS, of course, right now it doesn't work because they already modified the content. But I can do the same thing here back into 4326. Okay, so now this becomes 4326. And from here, I can do 4326 and then dot to, okay, CRS parentheses. And then from here, I can just say EPSG 3857. So I can do the projection and then I save the file, then it works. So for example, this one I say 3857B and run it. I hope it works. Okay, so now I'm going to open one last time here. This one doesn't work, so you need to remove it. Basically, it doesn't align with the data layer. Move it and zoom to this one. Okay, so one last time, let me open this one. I hope it aligns. Okay, coming back. So you need to do the projection rather than assigning a coordinate system. Do the TR2 CIs, then it's work. All right, so that's all for today. And I think I've released lab 4. You can start working on lab 4. So lab 4 covers the pandas, NumPy, and also GeoPandas. I think this time I only put 4 questions, but there are some sub questions inside. And it not take you too much time. You just use the example I provide in the lecture notebook. You should be able to utilize some of the sample codes and then to do lab 4. Okay, all for today. Any questions? If not, I will see you next week.